Alright, I am the human equivalent of the movie The Room, but I am going to get through this. Alright, so what I want to do is tie chapter 13 back into chapter 12. Or at least take advantage of having covered chapter 13 to go over a concept that we had to kind of brush past in chapter 12, namely the involvement of equilibria in reaction mechanisms. So, the first reaction isn't always the slow one. The examples I showed you in the videos on chapter 12, it was. But that is not the way the world works, neat and tidy and so on. Sometimes later steps are slow, and reaction mechanisms reaction mechanisms aren't particularly complicated in that case, but finding or relating the rate law to the reaction mechanism can be. So here we have an example reaction. 2 molecules of nitric oxide. That looks like it should be nitrogen monoxide, but that's an example of a molecule whose name has been grandfathered in just because they didn't feel like changing it. So 2 molecules of nitric oxide plus oxygen go to form 2 molecules of nitrogen dioxide. And the experimentally determined rate law is just K times the square of nitric oxide and times oxygen, which looks exactly like the reaction as written, except that termolecular reactions, or elementary reactions, I should say, are very, very rare. Remember, getting 3 things to collide, altogether is very uncommon. So instead, we look at this proposed mechanism. 2 molecules of nitric oxide going to form dinitrogen dioxide as a fast step, and then the molecule of dinitrogen dioxide combining with oxygen to form 2 molecules of nitrogen dioxide, and that being a slow step. It's not necessarily obvious how we're going to get from here to the actual reaction mechanism, or rate law, but you can bet your boots it's going to involve equilibria. So, yes, equilibria. When you have a fast reaction followed by a slow reaction, you're going to get a buildup of the intermediates, the products of the first reaction. And when you get a buildup of products, eventually you're going to get the reverse reaction. You're getting an equilibrium of some kind. Okay? So it's not A goes to B goes to C. It's A reaches equilibrium with B, B goes to C. And as B is slowly removed by C, the equilibrium keeps shifting to produce more B, until eventually both A and B have run out. So the actual reaction mechanism is that step 1 is an equilibrium reaction. So 2 nitric oxide in equilibrium with dinitrogen dioxide. And then you have the second step, which is slow and still a straightforward reaction of 2 nitrogen dioxide plus 1 oxygen goes to form 2 nitrogen dioxide. So now we can use these 2 steps as written to get to the experimentally discovered rate law. And in order to do so, we have to take a look at all 3 reactions. Yes, I said 3. We'll look at step 2 because it's the one that's not the equilibrium. That's nice and straightforward. It is going to be fairly easy to deal with. We can just treat it like we always have. Okay, it's a nice elementary step, no equilibrium. So rate 2 equals K2 times into O2 times O2. That's a lot of 2's. Rate 2 and K2 is because we're looking at the second step. You often deal with multiple steps, so it's easier to distinguish the rate of each step and the K, the reaction constant, for each step using those subscripts so that you don't get them confused. I recommend practicing your handwriting. Other than that, the into O2 and O2 is just an unfortunate coincidence. Now, the problem here is that into O2, dinitrogen dioxide, isn't in the reaction, and it's not in the rate law. It's an intermediate, so it shouldn't show up. Okay, so we have to find a way to get rid of it. And as a side note, I'm using concentration here. It's gases. You could use pressures just as easily. Concentration, pressure, the rate law looks fundamentally the same. The rate constants would be different, the rates would look different, but the reaction mechanism isn't going to change. You can use either one, so don't worry about that. Okay. But that said, let's go ahead and move on to the next step. Actually to the first step, the equilibrium, the one that's more difficult. That's what we use to get rid of into O2. And recall I said we had 3 reactions, and here are the other 2. They are both within step 1, the forward reaction and the reverse reaction. Okay, so the forward reaction has a rate that I've subscripted F instead of 1, is equal to Kf times NO squared. Then we have the reverse reaction, rate R, is equal to K negative 1 times N2O2. This is an elementary reaction in either direction, even though it is an equilibrium. So we can just treat it as an elementary reaction, give it those elementary rate laws without any difficulty. Now, because it's an equilibrium, the forward rate and the reverse rate are equal. But I want to stress the 2 rate constants, K1 and K negative 1, are not equal. They're not the same number. They don't even have the same units. Okay? The forward rate and the reverse rate are going to be equal. You're not going to have the same concentrations. You're not going to have the same rate constant. And it's going to vary with temperature all over the place. So those numbers, not equal. Just plain old-fashioned not equal. So definitely don't get confused by that. And that's why I went ahead and labeled it 1 and negative 1, so that you know they're both coming from step 1, but one is going forward, one is going backward. That is the normal convention for this, the way we normally label these things. Okay? But I just wanted to emphasize that over and over and over again. The rate constants here are not equal. So now, with step 1 in hand, we can go ahead and get rid of dinitrogen dioxide. Because we have the forward rate is equal to the reverse rate for step 1 is equal to K1 times NO squared is equal to K negative 1 times N2O2. So we just solve for N2O2 and we plug that into the top equation, into the rate law for step 2. Because that's the slow step, that's the overall rate for the reaction. So you just take K1 times NO squared equals K negative 1 times N2O2, and you solve for N2O2. And you get N2O2 is equal to K1 over K negative 1 times NO squared. And that's what you plug in to the second step's rate law. Rate 2 equals K2 times K1 over K negative 1 times NO squared times O2. And that, as we see over here on the right, that is the overall rate law for the problem. And thus, this mechanism is nicely consistent with the reaction as it's been proposed, and it handily eliminates the need for a termolecular elementary reaction. Now, at this point, you may be wondering about K2 times K1 divided by K negative 1. A constant multiplied by a constant divided by a constant is just a different constant. Okay, we don't have to get rid of all those things. You just collapse them down and call them K or K prime, or K3, whatever you want. It's just another constant. We had to get rid of N2O2. We don't have to get rid of all those different rate constants. All right, so now that we have that example, I'm going to show another example and walk through that one as well. All right, so here is our next example. 2 nitric oxide. Yeah, nitric oxide, what you gonna do? Goes to form N2O2 again, yeah. For the first fast step, then we have N2O2 plus hydrogen makes N2O plus H2O, water, for the slow step, and then N2O plus hydrogen makes nitrogen and water for a fast step. So first, what is the overall reaction? And then, what is the overall reaction mechanism? Okay, so I'm not going to try and write this out in my spreadsheet or my PDF, my slideshow maker. I'm going to do this by hand. So here we have all the steps rewritten. So the overall reaction, that means we're adding the 3 steps together to find out what reaction they add up to. So first thing you do is anything that appears on both sides of the arrows, in both products and reactants, it cancels out. Anything that appears on the same side of the arrow in different equations, different reactions, different steps, they'll add together. So N2O2 appears in the products on step 1 and in the reactants on step 2, so we cross it out. Then we have N2O, dinitrogen monoxide, appears in the products of step 2 and the reactants of step 3, so we cross that guy out. Nothing else appears on both sides, but here we have, in steps 2 and 3, we have hydrogen appearing in both steps and water appearing in both steps, so we're going to have to add those together. And so when you add all 3 steps together, what you get is 2 nitric oxide plus 2 hydrogen goes to form nitrogen plus 2 water. Now this definitely can't occur in a single step. This is not an elementary reaction, so it's going to need some sort of reaction mechanism. So what we do now is we look at all the steps to find out what that reaction mechanism is going to be. So now we turn our attention to the rate law, getting from this proposed mechanism to the rate law that it would require. Now we tidy things up a bit, and let's go ahead and mark down the steps, and here's the fast step, a slow step, and a fast step. Now, when you have a fast step after a slow step, it doesn't really factor into the rate law. You don't have to pay attention to it for that. I mean, it matters for the overall reaction, obviously, but you don't have to worry about rates and rate constants and so on. So we just ignore that. Instead, we have to focus on step 2. That's the slow step, so that is the rate determining step. That's where our rate law is ultimately going to come from. But it has that pesky dinitrogen dioxide in there, so we're going to have to take advantage of the existence of step 1 to go ahead and get rid of that. And this will look, very similar to what we did before. So now we give ourselves the rate from the second step. So rate 2 is equal to K2 times N2O2 times H2. Nothing too fancy there. It's an elementary step, so you're just multiplying by each reactant raised to its coefficient. So the rate is equal to the rate constant times coefficient raised, or concentration raised to the first power times the concentration raised to the first power. Step 1 is a little bit more complicated, but it will look like the previous example, because it's the slow step preceding a fast step preceding a slow step, excuse me, which means that it's actually an equilibrium, and that means that it's got a rate 1 is equal to K1 times the concentration of nitric oxide squared, and rate -1, that is the reverse rate for reaction 1, is equal to K -1 times the concentration of N2O2. Once again, we use the convention 1 and -1 to refer to the forward and reverse reactions. And because it's an equilibrium, fast step coming before slow step, rate 1 is equal to rate -1. It's in equilibrium. So with this information in hand, we can get rid of that pesky N2O2 over in the expression for rate 2. We clear a little bit of space, and now we just set things equal to each other. So rate 1 equals rate -1. So K1 times NO squared equals K -1 times N2O2. So you solve for N2O2, you get N2O2 equals K1 over K -1 divided by NO squared. Now we're just going to go ahead and plug N2O2 up into this expression for rate 2. And what you get is that the rate, and this is the overall rate, I want to emphasize that. The slow step, the rate determining step, is the overall rate for the reaction. So it's equal to K2 times K1 over K -1 times K2 times K1 over K -1 times NO squared times H2. And then we simplify that down, and what we're going to get is the overall rate of the reaction equals K times NO squared times H2. Instead of writing K2 times K1 divided by K -1, I just went ahead and collapsed that down. Constant times a constant divided by a constant is just equal to some constant. And if you were, instead of working from the mechanism to the rate law, if you were working from an experimentally determined rate law beforehand, this thing in the box is what you would see. You would have just the rate, not rate 2, not rate 1, not rate 3, but just rate is equal to a rate constant that you measured experimentally times NO squared times H2. So that's what you would see, and it's exactly the equivalent. Now let's go ahead and compare this to the actual steps. Okay, so we combine a couple of slides here, and we have the 3 steps and the overall reaction and the rate law for this mechanism. The rate law doesn't match any one of these steps, and it does not match the overall reaction. But you can sort of see how it comes right out of steps 1 and 2 combined. And once you get rid of the intermediate dinitrogen dioxide, you have the NO squared from step 1 and the hydrogen, the 1 hydrogen from step 2. And of course, the second hydrogen that you might expect from the overall reaction, that doesn't show up because it takes part in step 3 and therefore doesn't appear in the rate law. Likewise, the dinitrogen monoxide, the N2O, that shows up as a product of the slow step, so it disappears pretty much as soon as it's made, thanks to step 3 being faster than step 2. So it also, you don't have to take it into account, and it's not going to show up in the rate law. Now, these reaction mechanisms can get really complicated. Remember the nasty pictures you've seen. I probably won't be giving you anything more complicated than this on a test or on a homework, but just be aware that they can get worse. They can also get better. Don't expect them to get better, though, because I am cruel and mean at heart. Okay, so hopefully, with a couple of examples worked through like that, you'll be able to work these sorts of things on your own. Have a nice evening.